All right, we're back with the last part of the review. So this is 19.3. Solubility product constant is what we're looking at. So that's abbreviated K with the subscript SP. It is the product, so product is multiplication, of the concentrations of ions raised to the power equal to their coefficients, very similar to what we found for equilibrium constant. So the first question is, do all compounds have a product solubility product constant? And the answer is no. Not all compounds create ions. If you remember, something like glucose, which is made of only nonmetals, is actually, so the answer is no, because it produces no ions. It is what is called molecular. And so we also have silver chloride. Silver chloride does produce ions. So the answer is yes. And it's because it is ionic. So it produces ions. And then oxygen molecule, both parts of the element, the two oxygens connected to each other, double bonded. The bond is going to be shared electrons. So that would be a no, because it is molecular. All right, so let's look at what it looks like for the silver chloride, silver 1 chloride. So you have silver 1 chloride, and since this is having to do with producing ions, if you take silver chloride and put it in water, so aqueous, it will dissolve into silver 1 ion, a chloride 1 ion. So then when you write the solubility product ion constant, you get the concentration of silver ions times the concentration of chloride ions. So when solving for the solubility product constant, this is how you would write it right here. Okay, so let's go ahead and solve one of these. If you're given that silver 1 chloride, or sorry, silver 1 sulfide, I changed it on this one. If you're given that the solubility, so in this case, you'll notice that it's grams per liter. So that is a solubility. It is actually not KSP. So it's given as 2.84 times 10 to the negative 15. So that means that 2.84 times 10 to the negative 15 grams of this substance dissolves in 1 liter. So first step, go ahead and write the balanced chemical equation. So you write silver 1 sulfide, and in order for the charges to cancel, silver 1 is a +1, and you need 2 of them. So that's why I wrote a 2 as the coefficient. And then you have a sulfide ion. It has a 2 negative charge. So this is your balanced chemical equation. Then you want to write the solubility product constant equation, and that is similar to what we wrote up here for silver 1 chloride, except in this case we're writing silver 1 sulfide. So silver 1 sulfide, you're going to have the concentration of it, and it's going to be raised to the power of 2. And the reason for that is that the coefficient is 2 in the balanced equation, and that is why you need a balanced chemical equation before you write this out. Then you have sulfide ion, and there is no coefficient, so you can leave it as just 1 or not write anything there. Last, or almost last, you find the concentration of each ion. So if we know that the solubility is this, here's how I set it up. So concentrations are written as molarity. Molarity is moles per liter. So you will write down the solubility, which is grams per liter, multiply that by the inverse of the molar mass. So that is moles per gram, not grams per mole. So you invert it, and then you will get moles per liter, which is molarity. So step 1A, go ahead and find the molar mass of silver 1 sulfide, which comes out to 247.8 grams per mole. Then you plug the numbers in. So here is my given solubility. So that was given in the problem earlier, and then I divide by the molar mass, or just multiply by the inverse, same thing, and I get a solubility of 1.5 times 10 to the negative 17 moles per liter, or Moving on, we want to find the corrected concentrations for each ion. And corrected means I have to think a little bit critically about the actual equation. So if you notice that in the balanced chemical equation, and I'll scroll up here so you can see it, um, every 2 moles of silver requires 1 mole of sulfide. So when this compound breaks apart, it breaks into a 2-to-1 ratio between silver 1 and sulfide. So I wrote that here, that the balanced chemical equation states that for every 1 mole of sulfide, you need 2 moles of silver 1 ion at equilibrium. So to write this out, I would write my molarity that I found from the equation in step 3. And then I need to multiply that by 2 because it requires 2 times the amount of the other substance. So therefore, my concentration of silver 1 is going to be 2.29 times 10 to the negative 17. So that is double of what I found in step 3. Then the concentration of sulfide, since there is nothing to multiply it by, will just be the answer that I got in step 3. Last step is to solve for the solubility product constant, and that is using the equation I wrote earlier. I set it up here. I plug in my values from step 4. So for silver 1, I write it here. And then again, I have to still remember to write the power. It's still raised to the power of 2. Even though I multiplied it by 2 inside, I do need to raise it to the power of 2 on the outside. Then I multiply by the concentration that I found for sulfide ion. When I do that, I have my solubility product constant equal to 6.03 times 10 to the negative 51, which is a very, very, very small number. All right, so that is how to solve for the solubility product constant. Moving on, you can use that to predict if the precipitate will form. If you remember, a precipitate is a solid that falls out of solution when you mix 2 compounds together that are in aqueous states. So just one thing to note from the reading, and I just abbreviated it, is that the ion product, which is what we just found, or I'll show you how to find that, is if it's greater than the solubility product constant, a precipitate will form. But if the ion product is less than the solubility constant, then the precipitate does not form. So here's an example. So it says calculate the ion product. So again, this is the product of the ions themselves multiplied together of silver bromide. So this is a solution that you might do in a laboratory if we were at school. So silver 1 nitrate and potassium bromide mixed together. And of course, these are an aqueous solution. So you have 100 milliliters of 0.002 molar silver nitrate, and you're going to mix that with 100 milliliters of 1 times 10 to the negative 4 molar potassium bromide. Will a precipitate form if the precipitate is supposed to be silver 1 bromide when you mix the solutions? One thing to note is you're mixing 100 milliliters of one solution and 100 of another, so your total amount is going to be 200 milliliters. That will come up later. All right, step 1, you want to find the concentration of each ion. So that you're given a molarity of the original solution that you're pouring in, and then you're given the amount that you're going to pour in. So first step, molarity is written as moles per liter. Your amount that you're given is in milliliters, so you have to convert that first to liters. So that is 100 divided by 1,000 milliliters, or you multiply by 1 liter over 1,000 milliliters. Either way, this in the parentheses will give you 0.1 liters. All right, then you multiply that by the molarity, and what will happen is the liters here will cancel with the liters here. The milliliters here will cancel with the milliliters here, and you will get the number of moles of silver. Why do we need to do this? Well, the solution is 200 milliliters, and we need to figure out how much of our product forms in moles first, and then find the molarity of that within the product. So you follow that same process for the bromide ion. So 100 milliliters is of 0.0001 molar. I just converted it to a decimal. And that gives you 1 times 10 to the negative 5 moles of bromide. So now that you've done this calculation to find the number of moles, That's step 1A. 1B, now we're going to actually find the concentration. So again, this came up, and I mentioned this earlier, 200 milliliters is the total solution. So looking at the number of moles, I need to divide that by the number of liters of total solution. Again, in parentheses, I've converted 200 milliliters to liters by dividing by 1,000. So essentially, it's 2 times 10 to the negative 4 divided by 0.2 liters once I solve whatever is in this parentheses. That gives me a molarity of 0.001 molar silver, 1. And then I do the same thing for my bromide. And so now I have my molarities, and then from there, I can solve for my ion product. Ion product is I take the two amounts and I basically multiply them together. So to find the ion product, to compare it, I need to multiply the silver by the bromide, what I found in step 1B. So 0.001 molar silver multiplied by 5 times 10 to the negative 5th molar bromide gives me 5 times 10 to the negative 8. For my, I'll write it on the side, this is my ion product, not to be confused with the solubility product, which is here. So ion product is multiplying the molarities. Solubility product is the likelihood of them dissolving. So from the data table, and this is, you have to click on the reading up above, there's a link. You'll find that it's 1.8 times 10 to the negative 10. So one thing to note, and I wrote it here because sometimes we forget our math, that a smaller negative value when it's in the exponent, so negative 8 versus negative 10, right? So a smaller value means that it's a bigger value overall, which means that, therefore, the ion product, so this number, 5 times 10 to the negative 8, is actually bigger than the solubility product constant, which is 1.8 times 10 to the negative 10. 10 to the negative 10 is much smaller than 10 to the negative 8. So that means that it will be giving a precipitate based on the information I provided above. All right, and then the last section that I want to cover in this one is going to be something called the common ion effect. And so we use this to solve for unknown concentrations of a compound in a solution. When we do that, first you want to read the question, obviously. So here's the question. It says, determine the concentration of lead 2 ions. So that is the goal. It's in 1 liter of solution. So this is going to be helpful a little bit later, and I'll explain why. In a saturated solution, which means that everything is to the max of lead 2 fluoride, in which you add 0.025 moles of fluoride ions to the solution itself. So you're actually adding more fluoride than was there previously. All right. So the solubility product constant, not to be confused with the ion product. So that is the solubility product constant. You can find this in the data tables in the reading, but it's actually given to you right here as 4.18 times 10 to the negative 8. All right, so step number 1, you want to make sure you have a balanced chemical equation. I didn't list that as a step, but you do. So you write it like so. 1 mole of lead 2 fluoride will break into 1 mole of lead ions and 2 moles of fluoride ions, since there are 2 attached to the lead originally. All right, the solubility product constant is written this way. And so we go ahead and write it like this. And instead of knowing what the concentration of lead is, we're just going to replace it with a variable s. So in math, you replace it with x. So we do s. And if you remember, then it's going to be 2s for the fluoride, since it's double the amount of moles needed, or molarity. And then you're also adding an additional 0.025 moles. So yes, in this bracket, it should be molarity. So obviously S is molarity. And then 0.025, if you read it in the problem, you're going to say, well, it says moles. Well, you have to remember, this is in a saturated solution that is a total of 1 liter. So 0.025 divided by 1 is 0.025. So this is actually 0.025 molar. So it comes out to be the same thing. So the S is going to be representative of the concentration of lead ions. All right. One thing to note that's a little different than math is that 0.025 is a value, and 0.025 when compared to solubility product constant, the solubility product constant is going to be much, much smaller. We're talking about 10 to the negative 8, which was written up here, compared to 0.025. So therefore, the S, or the concentration of lead ions, is also going to be much, much, much smaller. That's what this means than the molarity that you add, or the moles you add of fluoride. So you're actually adding a substantial amount. So therefore, you can actually eliminate the 2s portion in the brackets for the concentration of fluoride. Now, I don't want you to be confused. You cannot eliminate this one because this one has to do with lead ions. In this bracket, if you're comparing the 0.025 to the 2s, that's 10 to the negative 8 compared to 0.025. That means that this is pretty negligible or very, very small. So I can just eliminate it. And so when I rewrite my problem, it looks something like this. So it's the concentration of lead, right, multiplied by 0.025 moles of, or molarity of fluoride that I add, squared. And the squared comes from the balanced chemical equation, the coefficient. All right, and then solving for the equation, you get the derivation here. So 4.02 times 10 to the negative 8 divided by 0.025 squared. And that solves for S, which is the concentration of lead to ions. And it's the concentration because, again, we are in 1 liter of solution. So this is the actual answer. Again, if you have any questions, go ahead and email me. You can set up a time if you want live instructing. I'm available between 8 a.m. and 4 p.m. every day. So you can email me anytime.